Hey, you guys, here's your first installment in Chapter 5. We have about half the chapter to cover in these slides. So Chapter 5 is about gases, and gases, of course, are extremely important because we breathe a gas. So when you want to go scuba diving or something like that, you need a gas tank, or I guess even like astronauts, of course, they need a gas tank when they go outside the spaceship. So let's talk about some properties of gases. We're going to be looking at things like pressure and volume, and amount and temperature and how they affect the state of the gas. So in this first slide, you see scuba diving, of course, because you have a pressurized gas in a scuba tank. In this picture is a picture of NO2 gas, which has a brown color. That's the same gas that you see in pollution, and it makes an area look brown. And then, of course, we have an airbag here, and an airbag has a gas in it that is created in basically an explosion, and that's nitrogen gas. There's an airbag, I believe that's sodium, has sodium azide in it. And then when this does it's switched on by that collision, that movement somehow, I looked it up once, but it has to do with like a ball moving or something. As soon as that forward collision comes, there's a trigger that happens, and then this reaction occurs, and then you get nitrogen gas coming out of there. And then, of course, it explodes right into the airbag. So it changes its volume. Actually, it didn't have any volume to begin with. This was a solid. And then when that comes out, you have a gas that has a volume at that temperature and pressure. So for let's look at our first slide here, just talking about elements that exist as gases. So here's your periodic table that shows the elements that exist as gases at 25 degrees in 1 atmosphere pressure. As far as our fill-ins, this is something that I would take from your guided reading, and just gives you some characteristics of gases. They assume the volume and shape of their container. They're the most compressible form of matter. They mix evenly when combined to the same container, and they have much lower densities than liquids and solids. So they're very spread out. So if you were to draw a gas in a container, it might just look like these, dots. And there's a lot of empty space. That's why you can walk through it. But that's why when the wind blows and all those move at once, they can definitely cause some damage because it's molecules moving at a fast rate, and a lot of them at once. So here's a table from your textbook showing some substances found as gases, again at 1 atmosphere and 25 degrees Celsius. So fun sheet number 1 is asks you some questions about, looking at a list of substances, which ones exist as gases at room temperature pressure. So pressure of a gas, what is pressure in general? Pressure is force divided by a unit area. So I can have pressure down on a very tiny point. Say this was a mass of some sort. There would be a pressure point, for want of a better word, a lot of pressure at this very small point because it's force over a very small unit area. Now, since pressure is force over per unit area, we can still use that for gases. Force, if you remember, is mass times acceleration. So as far as units of pressure, a Pascal is known as a Newton per meter squared. The Newton is the force. The area is a square meter. Now, an atmosphere and this millimeters of mercury and torr, this was a measurement of pressure using a barometer. Let's say here's a mountain, and then here is sea level. You would have this apparatus, this barometer, and there you basically just measure the distance of the mercury. And at sea level, apparently on the planet, at sea level, the measurement of pressure is 76 centimeters or 760 millimeters of mercury. Torr is the same unit size as millimeters of mercury. And then 1 atmosphere is at sea level, and that is in unit of atmospheres. So when you go up in altitude, your pressure decreases because there's less molecules of gas surrounding you if you were standing up here on the mountain versus down here, down at the bottom. Also, a unit of pressure is Pascal, like we just said there, and the conversion between pascals and atmospheres is that 1 atmosphere is 101.325 or 325 pascals. I'm thinking of 101.325 kilopascals, 101.325 kPa. Okay, so as far as thinking of pressure, the reason we have pressure on us is because there's a column of air on top of us. So if you think about this planet, I mean, there's air out here, and that air is actually pushing down on everybody, on the inhabitants, on the water, everywhere on the surface of the Earth. So at sea levels, 1 atmosphere, 4 miles up, it's a half of an atmosphere, and 10 miles up, it's 0.2 of an atmosphere. So check out fun sheet number 2. This is talking about being able to drink from a straw on Mount Everest versus sea level. Now, how do you study pressure and volume of the gas and its relationship? And this is a picture out of your book that is showing that's mercury. Apparently, mercury was a very handy substance here because it had a high density. It was a liquid, so you could put it into a tube, and then if you trapped some gas here, and actually, if you had a tube that was a closed tube and you put mercury in, there was air in there, so it trapped that air. Now, it doesn't matter what gas it is, whether it's air, which is nitrogen and oxygen, it doesn't matter. But the more mercury you put on it, the smaller the volume got. So the more mercury meant an increase in pressure, and then you would get a decrease in volume. Again, more mercury, smaller volume. And that's what that says right there. As pressure increases, volume decreases. So this is Boyle's law, that as pressure increases, volume decreases. So P goes up, V goes down. So this was showing this in this graph. That's an exponential relationship. Here's your volume. If I increase pressure going up this way, my volume decreases in an exponential fashion. So if I want a straight line to look at some type of relationship between pressure and volume, I can process the data in such a way, these values, to graph 1 over V versus P, and you get a straight line. And this is at constant temperature and constant amount. So what this means here is pressure is proportionally to the inverse in volume. So P is proportional to 1 over V. So what happens, now your book talks about these constants, is that if you multiply both sides by volume, you get, and you want to make it equal to a constant, that's what this constant is over here. So if you say P times V, I mean, because it kind of seems strange, it's proportional to 1. Well, that doesn't really make any sense, but I guess it does kind of, because when we say a constant in mathematics, that usually means it's a number. It doesn't change, it doesn't have a variable. So this is a number and it doesn't have a variable, so you can think about it that way. But what this also means is that when volume and pressure are altered, one has to accommodate the other. So if I increase pressure, then this volume will decrease to keep this situation true, to keep this part of the equation true. So that's why when you see this P1 times V1 equals P2 times V2, what that means is if I have a pressure, and you could choose it off of this graph up here. If I have a pressure of 0.3 atmospheres, and then I multiply that by 4 liters, because that's the volume that goes with that. If you look at that graph up there, and then I have the second pressure, which is 0.6 atm, and I multiply that by 2 liters. I mean, you'll notice 4 times 0.3 is 0.12. And then 0.6 times 2 is 0.12. So you see how they're the same number. So since they're the same number, they're related to each other, this relationship. And that's why when pressure increases, the volume has to change to keep the relationship true. Let's do an example here. If I have a sample of a chlorine gas and it occupies a certain volume at a certain pressure, and I change the volume, if the volume is reduced at a constant temperature and I decrease the volume, it looks like, I'd say my pressure is going to go up. So we were at 946 milliliters. Here's all of our information. We were at 946 milliliters. And at a certain pressure. And what happened is that the volume decreased. So this is kind of like a piston, if you can think of a piston or a syringe, where you have a sliding thing that I can push it down. And if there was a sample of gas in here, say at 946 milliliters, and then I pushed it down to 154 milliliters, then the gas that is in here is going to be under a greater amount of pressure. And that turns out to be 4,460 millimeters of mercury, which is quite high. So that's Boyle's law, and that's the relationship of Boyle's law of pressure and volume and at a constant amount in temperature. Now, what about volume and temperature? And here's kind of a little apparatus. Again, here's this mercury. You have some gas in here, and they put a glob of mercury in there, and then it traps the gas that was in there. Now, if it's at a low temperature, then it occupies a smaller volume than if it's at a higher temperature. So this is a study of Charles' law. So let's look at some graphs. As temperature increases, volume will increase also. So this is a Charles' law or Gay-Lussac's law, whereas temperature increases this way, you see a volume increase also. And it's a linear relationship. See all of these lines, these are just at different pressures. So it didn't really matter what pressure I ran it at. I still, and did this experiment, I still ended up with a linear relationship. And what was interesting about Charles' law is it helped to discover absolute zero. So at negative 273.15 degrees Celsius, that is absolute zero. So if you cool it to that much, theoretically, you could get a zero volume, which doesn't make any sense because there's actually mass of, and there's actually a gas in there. But if you could, that is what absolute zero would indicate. So volume is proportional to temperature. This is a direct relationship when you see it like this. So to make it an equal sign, you have to put a constant in there. That's what happens is when you want to make this equal, this constant has to be in there to make it equal. That constant can be anything. That constant is actually, in this experiment, you would take a volume and a temperature and divide it. That's the constant. You can choose any volume and temperature. Like I choose a volume and temperature up here on this one. That's going to be a constant. So I say V1 over T1 equals some constant. I don't know what it is, but I could just put it in there. That has to equal V2 over T2. So what that is saying is if I go up here to this graph and say I did a volume and a temperature and I multiply them and here I am. If I change one of those values and I change temperature, for example, I heat it up, then volume is going to have to go up in a proportional manner to keep this relationship true. So temperature, that's why temperature when you're studying gases must always be in Kelvin, because Kelvin is what makes it true. You cannot have negative Celsius, and because remember we can have negative Celsius and negative Fahrenheit, but there's no such thing as negative Kelvin. Kelvin goes to 0 K, and that it stops there. There is no such thing as below that. And you'll see why, because when you're on your fun sheet, if you try to do some of those problems and you forget to put it in Kelvin, you might end up with a negative volume because you're going into negative temperatures, which doesn't make any sense. So let's do an example. A sample of carbon monoxide gas occupies a certain volume and a certain temperature. And at what temperature will it occupy a different volume? Now you'll notice that the volume looks like it's decreasing. So if it's decreasing, this number has to go down. So recall there's Charles's law. Get all your information together as far as what's given, put your temperature in Kelvin, and plug in all the numbers and figure out what the new temperature has to be. And that new temperature has to be something lower. Right? So we put this together, put it in there, and make sure our units cancel. Yes, 192K is lower than 398K. Now let's keep on going. Avogadro's law, Charles' law, we did volume and temperature. Boyle's law, we did pressure and volume. Avogadro's law is discussing volume and amount. See, so when these experiments were done, you could only actually you can vary many parameters, but that's not a great way to do something because you really can't figure out what's causing the change. So in all of these experiments, variables or two parameters were changed, and then the others were kept constant. So if volume and amount are changed, then what's being kept constant has to be the rest of the variables or parameters, which is pressure, temperature. Because the four variables of our gases we're studying here is pressure, temperature, amount, and volume. So if you're studying volume and amount, then you have pressure and temperature left over. So what does this mean? When I want to make it to an equal sign, I have to have a constant there. This is a direct relationship, which means when amount goes up, volume goes up at a constant pressure and temperature. And that kind of makes sense. I mean, when you put more in there, it's got to get bigger in order to keep the same pressure and temperature. If you did not let it get any bigger, your pressure would increase and your temperature, it might get hotter. So here's our relationship for volume and amount using Avogadro's law. Again, this is a direct relationship. So what this is showing here in this figure is that you can have a certain number of moles of gas, and we could do molecules here, like we have 3 molecules of hydrogen and 1 molecule of nitrogen. That has to make 2 molecules of ammonia. So the more you put in, the more you would get out. So if we doubled this and we put in 6 molecules of hydrogen, we would have to now have 2 of nitrogen, and then that would bring us to how many? If we had 2N2, and let's talk about stoichiometry for a minute. 1, 3, 3H2, 1N2, and 2NH3. If I start with 6 molecules of H2, then that's going to go to 3 times 2 is 6 times divided by, it's 12, divided by 3 is 4. So it's basically, I just doubled, so I'm going to get 4 over here. So what I was using there was called the mole ratio. And what is being pointed out here too is what's called a volume ratio. Volume ratio. And the reason this works is because there is the same number of molecules of a gas under the same conditions. So in this case, if we have 3 moles, and 1 mole will make 2 moles. And that's the same thing for volume. 3 volumes and 1 volume will make 2 volumes. That's because a volume is related to a mole. I don't know if you guys remember that there's a video I put out there of the guy with the big fluffy white hair, and he said, I'm a chemist. And he was talking about Avogadro's number. And Avogadro's number was determined using gases. So if you have the same number of molecules, it's the same as the same number of moles. So just like mole or molecule, they're interchangeable. So if we do an example applying this, if ammonia burns an oxygen to form nitric oxide in water, how many volumes of nitric oxide, shame on us for using that, that would be nitrogen monoxide. So how many volumes of nitrogen monoxide are obtained from 1 volume? So I think we need a chemical equation here. 4 N's, I'm going to make sure it's balanced, and 12 hydrogens, yes, and then 10 oxygens. Yep, that is balanced. How many volumes of NO are obtained? Volumes, I guess we're saying liters, are obtained from 1 volume of ammonia. So if you have 1 of these, how many of these? Well, it looks like it's a 1-to-1 ratio. So I would think it'd be 1. It's 1-to-1 at constant temperature and pressure. So if it's 1 mole, it's 1 volume. So let's summarize these gas laws. We already talked about Boyle's law, which is pressure and volume. And pressure is proportional, if you remember here, pressure is proportional to 1/V. Now I want you to go down here and take a peek at this. There's a constant. Remember when we put a constant in here to make it into an equal sign? Once we make it into that equal sign, there's a constant here times that 1/V. But that constant turns out to be at constant amount, N is amount, T is temperature, and this R value is the gas law constant, which is 0.08206 liter atmospheres per Kelvin mole, and that number has to be in there to make this true. Charles' law, same thing. This is a constant, and that R has to be in there at constant amount and pressure to make this relationship true. That's volume is directly proportional to temperature. And to make it an equal sign, you need the constant, and there it is. Now, heating or cooling at a constant volume. So this is, if you notice here, this one up here was volume and temperature. This is pressure and temperature. Same idea. Pressure is directly proportional to temperature. So if you increase the temperature, you'll get an increase in pressure at a constant volume and amount. Avogadro's law is volume is directly proportional to amount. The more you put in, the higher the more you put in, the higher the volume. So this picture is showing more gas being pumped in, and the volume responds as such, keeping a constant R and temperature and pressure. So this all comes together to make the ideal gas equation. The ideal gas equation combines Boyle's law, Charles' law, and Avogadro's law. So if pressure is inversely proportional to volume, and then when we make it into an equal sign, we brought it over to the other side, and volume is directly proportional to temperature, temperature has to be on this side of the equation. Volume is directly a proportional amount, has to be on this side of the equation. And the only thing is missing here to have an equal sign is this R. So this is PV equals nRT. So that this slide was going through the same thing, showing how volume was related to temperature and pressure and amount. R is this gas constant. So this is PIV inert. You've heard that before. That's PV equals nRT. R is the gas constant, which is 0.008 liter atmospheres per Kelvin mole. So that R is always used here. And in order for that R to work, you need T in Kelvin. I mean, that's how the R was derived. The R was derived using measurements of pressure in atmospheres, volume in liters, N in moles, and temperature in Kelvin. So at ideal conditions, and those ideal conditions are low, high temperature and low pressure, you put all this in and you get PV, I'm going to rearrange, over NT equals R. And it will always equal R at low pressures and high temperatures. That's called the ideal gas equation. It's ideal gases behave this way in ideal conditions. If you put them under non-ideal conditions, then you end up with gases that are kind of protesting. They're like, it's too small of a space. My pressure's going up. I'm freaking out. So there's things going on that's non-ideal, and this R would no longer apply. It would actually, the R would apply, but you would have to do some correction factors to this equation, and that is in towards the end of the chapter. So try fun sheets numbers 3 through 6. Now we've gone over the gas laws, and those questions address the gas laws: Boyle's law, Charles' law, Avogadro's law, and so on. So as far as STP is concerned, that's the conditions at 0 degrees Celsius and 1 atmosphere of a gas. So standard temperature and pressure, that's just a definition that we use to be able to compare gases to each other. So at STP, 1 mole of an ideal gas occupies this volume. Don't ask why, it just does. That's all there is to it. And the volume that a gas occupies is dependent upon its pressure and its temperature. So remember, PV equals nRT. So we did PV equals nRT a second ago, and we said, and I was talking about that R was 0.08206. Well, you will get 0.08206 if you put in a pressure of 1 atmosphere, a temperature of 0 degrees Celsius or 273.15 K. Mole, this is N would be 1 mole. And then if you solve that, you would find that the volume is 22.414 across the board, no matter what gas it is. Okay, and that's what I was just showing you right here. So there's the R as derived with these values. So given that information, now we can use PV equals nRT to calculate something like the volume of a gas at a certain temperature and pressure and of a certain amount. So using PV equals nRT, and make sure to put your temperature into Kelvin, pressure should be in atmospheres, but N is always in moles. So since we knew it was hydrogen chloride, we converted hydrogen chloride from grams to moles, and then plugged it in. And you see everything cancels out properly as it should using the ideal gas constant. And you get a value of 30.7 liters for the volume of that gas. Now try fun sheet number 7. There's a problem like that here, very similar. Now let's think about something else here. I mean, as far as light bulbs are concerned, I mean, these types of light bulbs are kind of going by the wayside because they use so much energy to have them glow like this. So this problem is talking about argon, and it's an inert gas used in light bulbs. So there's a gas in here. It's at a very low pressure, but it is argon. And it's used to retard the vaporization of the filament, because when this is heated to high temperatures, it actually starts to vaporize, and that's why the filament would break and then your bulb was burned out. A certain light bulb containing argon at 1.2 atmospheres and 18 degrees Celsius is heated to 85 at constant volume. You'll notice these light bulbs are constant volume. What is the final pressure of the argon in the light bulb? So it looks like, remember, we're holding volume constant. It's a bulb. R is constant. And N is constant because there was a certain amount of gas that was trapped in here that has not moved and has not left the container. So what we can do is use the P over T. This is pressure and temperature. You had an initial set of conditions of pressure and temperature, and then you change the temperature, and you want to solve for the new pressure. So by plugging in all those numbers and making sure your temperatures are in Kelvin, we get a new pressure to be higher, which it should be because we heated it up. So when you heat up a gas, it moves faster, and pressure by definition is the collisions of the gas with the walls of the container. So you're going to get more collisions when it's hot. So as far as density of gases is concerned, I mean, density, if you think of it, now what's weird about this is that you can have a gas, and there's a density associated with that gas. I'm going to draw two of them. It's going to make it a different color. There, check it out. Now I've got two gases in here, and they're different. So let's talk about density of gases first, and we'll just look at the calculations. Now your book does a little bit of what's called a derivation of a formula from other formulas. Now we know that D is equal to M over V. We know that. Now as far as this mess here, I mean, where did this come from? This M is the molarity, not molarity, I'm sorry, molar mass. Molarity is the big M. This is like a cursive M. So where M is the mass of the gas and M is the molar mass of the gas, we can use this density equation to figure out, we want to know the density of a gas based upon its conditions. So here is a density, here's molar mass. I think we're going to rearrange this. So you can determine the molar mass of a gas if you know the density of it. So I guess, see, now think about experimentally. Here you have it, the density. Let's go back up to my pictures here. If we have a volume of a container, right, and we could figure out the density. Now density is equal to M over V. So if we knew the volume of the box and then we knew the mass of the gas inside the box, we could calculate the density of the gas inside the box. Then we could use that density down here in our equation to figure out the molar mass of the gas, which is like an identifier. So let's check it out. Let's do an example of this. If we have a certain volume of a gas, we have a volume, we have a mass, we have a pressure, and we have a temperature. What is the molar mass of the gas? Now we know density is equal to mass over volume. So here's a mass of the gas, and then the volume was given because that's the size of the vessel. Now we have a density. We can plug the rest of our things in. This is your gas constant, this is the temperature, this is the density of the gas, and this is the pressure surrounding the vessel. So if you go ahead and do all your canceling, and then you end up with a certain molar mass of a gas, and it helps to identify gases like if you didn't know what it was. So that's what this problem is about. If a chemist synthesized a greenish yellow gaseous compound of chlorine and oxygen. So you know it's chlorine, but you don't know how many, it's oxygen. You don't know how many, but you can determine the density like on the previous problem that we just did, and at a certain temperature and pressure. The goal is to calculate the molar mass of the compound and determine its molecular formula. So just like we learned on the previous slide, molar mass is equal to the density of the substance, And then you got your RT and P. Put all those together and you get a certain molar mass. Or from the density given, we know there are 7.71 grams of the gas in 1 liter. So this is something you could do here too. Mass of the compound over moles of the compound. So grams per mole, that is molar mass. From the given density, we know there are 7.71 grams of the gas in 1 liter. So what can we do with that? What we did with this is we went ahead and used the ideal gas equation to figure out the number of moles of the gas, and that can go right here. And we have the grams. And you get the same answer as you did on the previous slide. So when you're trying to solve problems, I mean, I like this way that the molar mass was was dependent upon the density and the other parameters, but we basically did the same thing just in 2 different steps. So the molecular formula of the gas, what is it? With a molar mass of 67.9 grams per mole. Well, if you just play with molar masses of the individuals, you find out it's got to be ClO2, because a chlorine weighs 35.45, and then 2 oxygens, 16 times 2. If you punch that on your calculator, you get 35.45 plus 32, and you get 67.5. So that would be the molar mass, or the formula, molecular formula of your gas. So you see how handy all this is to help study the world, basically, because if you create a gas you don't know what it is, you can measure things about it and figure out what it is.